The region of space around the nucleus where the probability of finding an electron is maximum is called an orbital. Whenever the n value will be increased, that time energy and size will be increased. Each subshell will be having different numbers or different values of L represented by different symbols. How to calculate the radial node? This is the formula n minus L minus 1. Hello everyone, I am Harshita Bhavasar from Vidhyaashram PU College, Temple of Excellence. So, today we shall continue the next session, that is session 6 for the chapter structure of atom. In the last class, we have discussed about Bohr's model of hydrogen atom and explanation of line spectrum of hydrogen and dual behavior of matter. Okay, today we will discuss, that is, orbitals and quantum numbers, shapes of atomic orbitals. Okay, so today we are discussing about overall orbitals and quantum numbers. So first we will understand what is atomic orbital. So before the atomic orbital, how it has been came into the concept of atomic orbital, we know that we have seen Bohr atomic model, and there are so many limitations of Bohr's atomic model. That is, he could not explain about the wave nature of radiation, right? And he told that around the nucleus there are circular path, we will call it as orbit, right? But Heisenberg showed some uncertainties in that, and he told there are an imaginary line, not a circular path. And also they gave about their existence and also about their explanations. It led to into the discovery of quantum mechanical model. What is quantum mechanical model means? Branch of science which is the study of motions of microscopic objects. And also Werner Heisenberg and Elwin Schrödinger gave an equation for hydrogen atom. So after that they gave the quantum mechanical model. In that, important feature is about atomic orbitals. So we'll see what is atomic orbital. The region of space around the nucleus where the probability of finding an electron is maximum is called an orbital. What he told? If this is a nucleus, this is the first orbit. If this is the second orbit, okay. If we consider only the hydrogen, this orbit only existed, this will be not present, okay. In a hydrogen atom, 2 electrons or 1 electron will be present. If we are having more than 1 electron, if we see s orbital, 2 electrons capacity will be there. This is orbit. The finding the probability of an electron between the nucleus and orbit, will call it as orbital. That orbital will be known as atomic orbital. Once again, the region of space around the nucleus here, where the probability of finding an electron, this electron is maximum, is called orbital. Okay. Then what are quantum numbers? There are a set of 4 quantum numbers which specify energy, size, shape and orientation. Okay. There are 4 quantum numbers. It will show or it will specify the energy, size, shape and orientation of an orbital. Of this orbital, it will specify the energy, size, shape and orientation. Okay. What are those quantum numbers means? First one, principal quantum number, and its symbol is small n. Next, azimuthal quantum number, that is small l. Magnetic quantum number will designated by ml. Next, electronic spin quantum number, that is m. Yes, these are the 4 quantum numbers. Next, we will see first what is principal quantum number. The principal quantum number n is a positive integer, okay, with value n equals 1, 2, 3, so on. What is positive integer? An integer with a positive sign, right? the principal quantum number identifies the shell and it determines the size and energy of the orbital. What it determines, we have seen 4 quantum numbers which will determine about energy, shell, size, shape, like that. So here principal quantum number, which is a positive integer, which will be denoted by n, it will be identify the which shell and determines the size and energy of the orbital. Okay, which how it will be identify the shell, like n equals 1 means first shell, first energy level, like that. Okay, size and energy of orbital increases with increase in value of n. Whenever the n value will be increased, that time energy and size will be increased. That we know. Okay, if n1 will be this much size, n2 will be this much size. Then size will be increased, automatically energy will also be increased. Okay, this is the overall representation n. We have considered 4 level here, 1, 2, 3, 4. Okay, it will be keep on continuing. Shell number we will designate it, we have seen that K, L, M, N, this is also keep on continuing. Then number of orbitals in a shell. How many number of orbitals in a shell can be accommodated? That will be calculated by n square. N is 1, then 1 square is 1. N is 2, then 2 square is 4. N is 3, then 3 square is 9. N is 4, then 4 square is 16. Okay. Then maximum number of electrons can be accommodated with that orbital. That can be calculated by 2n square, means whatever we have taken this n square will be multiplied by 2. Each orbital can be containing 2 number of electrons. Okay. See here, 2 into 1 square, that is 2 only. 2 into 2 square, that is 8. 2 into 3 square, that is 18. 2 into 4 square, that is 32. Okay, this is the principal quantum number. How many number of orbitals in a shell can be noted and how many maximum number of electrons can be seen in an orbital, like that we have explained. Okay. Next is azimuthal quantum number, that will be designated by small l. Azimuthal quantum number is also known as orbital angular momentum or subsidiary quantum number. It will be called with 2 different names, that is orbital angular momentum or subsidiary quantum number. It defines 3-dimensional shape of the orbital. Okay, it defines 3D orbitals. We know that we cannot assume that in a 2D shape. What we will write in 2D shape only, but the actual picture will be in 3-dimensional shape of the orbital. For a given value of n, L can have n values ranging from 0 to n minus 1. Okay, this is the range the already predicted for n value. Okay, that is for given value of n, the possible values of L are it will be equal to 0, 1, 2, 3, so on. The end will be n minus 1. 0 to n minus 1. This is the range we have explained here. Okay. Next, each shell consists of one or more subshells or sublevels. Each shell means a main shell energy level will be consist of subshells, one or more subshells or sublevels will be containing. Thus, n equals 1, L equal be 0. Okay, when the value of n will be equal to 1, then value of L will be 0, then only one value will be there. The only one level will be present, that is S level. When L equal to 0, that level will be only S. Okay. When n equals to 2, L equals to 0 and 1. 2 values will be seen, like 2 sublevels will be seen, that is S and P level. 2 sublevels or subshells, these are S, P, D, F are subshells. We know that here for n equal to 2, L will be having 2 values or 2 sublevels, that is S and P level. When similarly n equals 3, L will be 0, 1 and 2. 3 values, 3 sublevels, that is S, P and D level. Okay. When n equals 4, L equals 0, 1, 2 and 3. There are 4 values, 4 sublevels overall SPD and F level. Each subshell corresponding to different values of L are represented by different symbols. Each subshell corresponds to different values. Okay, we have seen here each subshell will be having different numbers or different values of L represented by different symbols. These are the symbols we have noticed. Next, here also we can see the azimuthal quantum number with the notation of symbol. When value of L will be 0, the notation of symbol will S, that is sublevel. When L equals to 1, that is P, L equals 2, D, L equals 3 is F. This table is very much important when you are doing the problems based on the orbitals. So you have to remember this table. Next, magnetic quantum number, that is will be designated as ML. It gives information about the spatial orientation of the orbital with respect to standard set of coordinate axis. Okay, it will explain about the spatial orientation of the orbital. For any subshell defined by L value, 2L plus 1 values are possible. Okay, for any N value we have represented L value. For given L value, we are representing for ML value, they ranging from 0 to 0 minus 1. Here we are ranging to 2L plus 1 for calculating magnetic quantum number. For each value of L, ML will be minus 1 to 0, minus 1 to 0, then 0 to plus 1. Okay. Thus, when L equals 0, M equal be 0, only one orbital will be having or one value or sublevel, like that. When L equal to 1, M will be minus 1 to 0, 0 to plus 1. Overall 3 values, that is 3 orbitals. When L equal to 2, M equal to minus 2 to minus 1, 0, plus 1, plus 2. Overall 5 values, 5 orbitals. Similarly, L equal to 0, M equal to be minus 3 to minus 2, minus 2 to minus 1, then to 0, plus 1, plus 2, plus 3. Overall 7 values, that is 7 orbitals. See, we know that shell will be later categorized to subshell. That subshell is S, P, D and F, right? So overall orbitals 1, 3, 5 and 7. These are the orbitals, right? First shell, then subshell. In subshell S, P, D, F, S will be accommodate one level, one subshell, and this P will be 3, D will be 5, F will be 7. Then one level will be containing or accommodate 2 electrons, S 2 electrons, P 3 into 2 6 electrons, D 5 into 2 10 electrons, F 7 into 2 14 electrons. Okay, the capacity of that orbital will be containing so many electrons. These are the information about magnetic quantum number. How it has been 1, 3, 5, 7 I have shown here. Okay. Next, electron spin quantum number. Okay, that will be designated by MS. It refers to the orientation of the spin of the electron. How the spin will be oriented for the electron? Here it will be showed. It can have two values, that is plus half and minus half. Plus half will be clockwise direction, minus half will be anti-clockwise direction. Okay, these are called two spin states of the electron are normally represented by two arrows, spin up and spin down, means spin up, spin down. One orbital or one shell will be accommodate two electrons, so spin up and spin down. the permissible values of quantum numbers for atomic orbitals. In this table, you can see all the quantum numbers value. When n will be 1, L will be 0, M will be 0, then subshell notation 1s, number of orbitals only 1. S means subshell will be only 1. When n equals 2, L equals 0, M equals 0, 2s, subshell will be 1. Again, when n equals 2, L equals 1, that is minus 1, 0, plus 1, 2p orbital will be 3. We have seen that p orbital contains 3 sublevels. When n equals to 3, L equals to 0, M equals to 0, that is 3s notation only 1. Whenever the s, it will be 1. Whenever the p, it will be 3. Okay. When n equals 3, when n equals 1, when m equals minus 1, 0, plus 1. Then 3p orbital, that is number of orbitals will be 3. Likewise, when n equals 3, L equals 2, minus 1, 0, plus 1, plus 2, 3D level, number of levels will be 5. 1, 2, 3, 4, 5. Okay. When n equals 4, L equal to 0, M will be 0, then subshell level 4s, number of orbitals will be 1. When similarly, when n equals 4, L equals 1, minus 1, 0, plus 1, 4p, 3. See, n equals 4, L equal to be 2, minus 2, minus 1, 0, plus 1, plus 2, 4d, 5. Okay. When n equals 4, when L equal 3, that is minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Overall 7. 1, 2, 3, 4, 5, 6, 7. Then it will be in 4f, overall orbitals will be 7. Okay. By this table, we can see overall all the quantum numbers, how it will be help for the number of orbitals except spin quantum number. We have not shown here spin quantum number. Next problem, using SPDF notations, describe orbital with the following quantum numbers. See, using the SPDF notation, we have to calculate or we have to write down for which orbital it will belong. Okay. We know that L equals 0 means S orbital, L equals 1 means P orbital, L equals 2 means D orbital, L equals 3 means F orbital. This is our basic information. This we have to implement to this problem. Okay. N equals 2 means that is second orbit. Okay. L equals 1 means P. N equals 4 means fourth orbital. L equals 0 means S. Likewise, N equals 5, fifth. L equals 3 means F. N equals 3 means 3. L equals 2 means D. When we cross check, see 2, 1, 2P here, 4, 0, 4S, 5, 3, 5F, N 3, 2, that is 3D. For which orbital it will belong? Like this we have to calculate. This is a simple problem and also like this problems you can see. Next, after all seeing the quantum numbers, we are going to explain about the shapes of atomic orbitals. We know that there are 3 kinds of orbitals or 4 kinds, but we will explain about S-P-D orbitals. First we will look up the S orbital. For S orbital, L will be 0 and hence M can have only one value, that is M will be 0. Right. This means that the probability of finding electron in S orbital is the same in all directions at a particular distance. Right. It is in spherical in shape. It is a nucleus. See here, the overall, the finding of the electron is equal in all the shape. Okay. Nucleus, 1s and 2s orbital. Here, 1s, 2s and 3s orbital. This is the overall S orbital, its shape we have to find out. In other words, s orbitals are spherically symmetrical. It's look like complete circle in all the direction. The distance will be same. That's why we are telling it is symmetrical in nature. Next, p orbital. For p orbital, L will be equal to 1. M can have 3 possible values, that is +1, 0 and -1. This means that there are 3 possible orientations of electron cloud in a p subshell. 3 orientations are there, correct? Px, Py, Pz. These are the 3 orientations. The 3 orbitals of a p subshell are designated as Px, Py and Pz respectively, along with x-axis, y-axis and z-axis. Okay. Each p orbital is thus dumbbell shaped. See here, this is x-axis. The p orbital, whatever the p orbital is there, it is along with this x-axis. So we are calling as px. Here, this is the y-axis. The p orbital is along with y-axis. That's why py. Similarly, z orbital, that is pz, is along with z-axis. That's why we'll call it as pz. The 3 p orbitals are aligned along perpendicular axis. This is y, this is x and z. We know the coordinates axis. On that, we have aligned the px, py, pz orbitals. Okay. Next, d orbital. For d orbital, L will be 2, M will be 0, +or -1, +or -2. Overall, 5 orbitals. D orbitals have 5 orientations. That is, there are 5 d orbitals which are named as dx, dy, dz, dz square and dx square minus y square. Okay. This is dxy, xy, d orbital, that's why dxy, dyz, okay, dxz and x square minus y square. Here dz square. Okay. It will be in a ring shape. Okay. So overall, this looks as overall double dumbbell shape. 1 dumbbell, 2 dumbbell. Like double dumbbell shaped. Next, notes. The region where probability of finding electron is 0, that we'll call it as node. Node may be angular or radial. First we'll look at what is node. Here one orbital is there, right? This is nucleus and this is orbital. Where this white region is present, nowhere that orbital is not present, the electrons, probability of electrons will be 0. That place we'll call it as node. Okay. It may be angular or radial. First we'll see what is radial nodes. Radial nodes occur when the probability of finding electron is 0 in a spherical region. In a spherical region, the probability of electron is 0, we'll call it as radial nodes. How to calculate the radial node? This is the formula n minus L minus 1. By using this formula, we can calculate the number of radial nodes. Next, angular node. Angular nodes occur when there is a plane where the probability of finding electron is a 0. See, one of the difference in between these two is the probability of finding electron in a spherical region is radial node. The probability of finding electron in a plane is known as angular node. You can observe the plane here. See, this is a plane where the probability will be of finding electron will be 0. See here, these nodes, if you pass a plane, it is a nodal plane. At that point, the finding electron will be 0. Okay. Number of angular nodes will be L. If you find out L, it will be equivalent to angular nodes. Okay. I hope you have understood whatever I have taught today. In the next session, we will find out electronic configuration of atoms, filling up of orbitals in atom, stability of completely filled and half filled subshells. Okay. So thank you everyone.